So this video is about an application of Newton's second law of motion, and this is one that involves pulleys. So what if we have a pulley in our system and there's a string going over a pulley and the force, is kind of changing direction because of the pulley, which is what pulleys do, it changes the direction of the applied force, right? So what do we do? So we're asked to solve for acceleration, we're asked to solve for tension. How do we go about doing that? So first of all, what I want to do is I want to look at kind of the free body diagram that we can make with the system with pulleys. So we're going to consider a very simple system, and here's our pulley, and we're going to assume that this pulley is massless and frictionless. Okay, so massless, frictionless pulley, and we'll also use a massless string. So we're going to really simplify this down. Okay. And we have two blocks, hanging over this pulley, and let's see, maybe, let's just go ahead and do it this way. So let's say this block is M2, this block is M1, and M2 is greater than M1, okay? And how do we do a free body diagram for this? So you can imagine, looking at all the forces here, we have this downward force, which would be M2 times the acceleration due to gravity. And then we have an upward tension acting on it. And on this block, we have this downward force of M1 times the acceleration due to gravity. And then we have this tension acting on it. These vectors are not to scale. But what you'll notice is, if we imagine this tension, it's going to go up here and then kind of down here. This force, is going to cause an upward force here and downward force here. And so the problem with the pulley is that our forces will change direction because of the pulley. And so it makes it very hard to set a coordinate system. If I make up positive here and gets redirected, down will be positive on this side. So what we do, or at least what I do, is I imagine I take these two blocks, I kind of grab them, and I swing them out, and so that I form a straight line. And so I reimagine it in terms of N1 being maybe over here, M2 being over here, and I kind of make this all one system. So I got to draw a dot box or oval around this. That's all one system. And this would behave the same way as if I had two blocks kind of tied together horizontally, and I exerted a force in this direction of M2G, which is where that comes from, and I exerted a force in this direction of M1G, which is where that comes from. Okay, this simplifies the system a lot. Now notice I don't have tension. Tension's working inside here, and so I can kind of ignore it for right now and then come back to it later. So, the free body diagrams for a pulley system, they work a little bit differently. At least I work a little bit differently. So let me show you how this works out in a problem. And what I just showed you is called an Atwood machine. Okay, so an Atwood machine has our pulley, and then it has two blocks going around this pulley. And let's put some numbers here. So maybe this block would be 50 kilograms, and this block is 20 kilograms. Okay. And we know just from looking at this that it's going to accelerate downward this way. Okay, there's a heavier block on one side, if there's frictionless and massless, and it's going to accelerate down this way. And so I kind of reimagine this in terms of having these two blocks and the 20 kilogram block over here and the 50 kilogram block over here. And I have 20 kilograms times, I'm just going to use 10 meters per second squared on this side, so maybe 200 newtons pulling this way. And then on this side, pulling in the opposite way, I'll have 50 kilograms times 10 meters per second squared. So I'll have 500 newtons pointing, the opposite direction. I'm going to make this way positive. Okay. And usually, there's two questions that we want to answer. We want to know, hey, what's our acceleration? What's the tension in that rope? Okay, so what this allows us to do, this allows us to get the acceleration, because now what we can say, 200 over here, now what we can say is that our net force is going to be equal to 500 newtons minus 200 newtons. Okay, so this will give us 300 newtons, right? And that in turn is going to be equal to the total mass times its acceleration. So the total mass will be the combination of the 50 and the 20. So what I'll get is I'll take 300 newtons is equal to a total of 70 kilograms in this case, times what A is. I can solve for acceleration. If I solve for acceleration, I would get 4.29 meters per second squared. Okay, so I have my acceleration. That's pretty cool. I don't even have to worry about the tension at all. The mathematics is very straightforward, very simple. I just have to keep, in mind for these types of problems, what forces are acting on the 20, what forces are acting on the 50, what direction that they're going in. Okay, but I did want to solve for tension as well. So now what do we do? Well, we take one of these two. It doesn't matter. Honestly, it doesn't matter which one you pick. Okay, so I'm going to solve for tension over here. And here's the thing. The tension is going to have to be the same on both sides. And the acceleration of both these blocks has to be the same. Okay, so really all I have to do is I zone in on one of these blocks. I'm going to do the 50. Okay, so the 50 kilogram block, as Barry said, it's going to be 500 newtons of the weight, and then the tension is pulling up. Okay, once again, I'm going to go back to net force, which in this case is going to be the 500 newtons downward minus tension is going to be equal to 50 kilograms, because remember, I'm only paying attention to this one block here, 50 kilograms times its acceleration of 4.29 meters per second squared, which I solved for in the previous problem. Okay, the previous part of the problem. And rearranging a little bit, we get tension is going to be equal to 500 newtons. This whole thing is going to be minus 214. Okay, extra sig fig. Okay, and whoops. Oh my goodness. So here, sorry about that, guys. Let me draw this back up here. Okay, so I subtract these two, and I'm going to get 286 newtons. And it's always good to ask if this makes sense. All right, so I'm claiming that the tension is 286. We know that the system will accelerate downward, so this tension should be less than 500, which it is, okay? And then on the other side, the tension should be greater than the 200 pulling down here, and it's doing that too. So this is consistent. It's going to have the same tension throughout. It's going to produce the same acceleration on both sides. You can check this if you want. Doesn't matter which one you choose. You just still get a tension of 286 newtons. And so that's how we do with pulleys, guys. And I can have more complex examples. We'll go over this in class of maybe, we'll have a ramp. This will be fun, right? A ramp, and then maybe a pulley, and then a mass hanging down. But, all we have to do is keep in mind, okay, well, we have, the FG over here. We have maybe the force of friction and the force parallel on this side. And we can still do a free body diagram. We can still do a free body diagram where you have these two masses. And now, we'll have the force of friction. We'll have the force parallel. And then we'll have FG. So anyway, this can be easily applied to more complex situations. And we will go over that in class.